Okay, and so you were mentioning a couple of theories and stuff that involved infinite spaces. Could you elaborate on that a little bit and maybe make it a little plain so like we lay folk can understand it too?
Sure. So I'm going to talk about a vibrating string. So that's a one-dimensional string that you like a violin string, you pluck it. Now, that string is made out of an infinite number of points. So when you pluck the string, point A has to know where to go, and so does another point, point B, somewhere else. There's an infinite number of points there. That is, in a string, there's an infinite number of degrees of freedom. Well, wait a minute. How many degrees of freedom are in our everyday space in which we live? Well, 3. Up, down, left, right, front, back. Well, okay, so those are the degrees we have. But think about it a little bit further. Each point on a string, and actually each point on you too, but each point on a string has a degree of freedom, okay? It can go up and down, but its neighbor point, well, can it do? Well, you could say, well, because this one pulled on it, that one will go up too. Yeah, but, okay, the key is that it didn't have to. It could have gone some other way, okay? So what is done here is that we have a function which has the height of the string over some points, and since we have an infinite number of points, there are an infinite number of values of heights it could have. That is an infinite dimensional space. And mathematics takes out of all the infinite dimensional space and picks out a nice shape, like a string, a plucked string, and that comes from, how does math do that? And it comes from Newton's laws, or physics. Physics gives us guidance as to what all those points, all those degrees of freedom are doing. Now, you may recall I said something about showing there exists a solution without ever solving anything. That's when I start working with all those degrees of freedom. And I can show it's inevitable if you have some equation, let's say for the violin string, out of all the deformations you could ever imagine, out of that infinite dimensional space, the only one you're ever going to see is exactly that vibrating string. That's how you solve and show existence and uniqueness in math. It sounds bad, but it's not. It's not. So some of the intuition and ways of going about it are very nice and occupy some of the central themes of modern physics, done since, let us say, the 1500s, and even before. And these sort of ushered in sort of this golden age in which we're living right now.
Okay, now when you're talking about infinite choices, like three-dimensionally instead of just line of stuff, can this or has this ever been applied philosophically somehow?
I'm gonna answer that question's above my pay grade. What I can say is I do think mathematicians are a little bit nature's lawyers. That is, we can say what you can do, and we're good at trotting out the fine print and where it applies and where it doesn't apply. And I think that's a real good role of the mathematician, is to when things apply, when things don't apply, because then you know a model really well, when it applies, when it doesn't apply. And so this is really, I think, where we earn our keep, is that somebody has a physical model, someone goes ahead and mathematizes it, then you could say, well, what are the ranges of applicability of this mathematical model to this physical phenomenon? When do you see phenomena that model will no longer explain, but you can quantitatively say when that occurs?